Okay, so we've talked about the first two components of a decision problem, the likelihood part of the component, which quantifies what the data say, the prior part of the decision problem. So that's this bit here. Yeah. And now we're going to talk about, the prior part that quantifies how basically how plausible the different classes are before you saw the data. And now we're going to talk about the last part of the problem, which is the loss function, which says how bad are different mistakes. And that's, so I'm going to look at this vignette here about the two-class decision problem. So I think this is a vignette that's most, that's probably mostly best read. So I'm not going to go over all of it in detail. I encourage you to read the details. But the basic idea is that we need to assign costs or losses to the different possible outcomes that could occur in a decision problem. And then we can do calculations that try to minimize our expected loss. Okay, so that's the basic idea. Is we're going to specify the losses. So let's think about what the possible outcomes are in the disease diagnosis problem. Okay, so in the disease diagnosis problem, we're trying to decide whether the individual is diseased or normal, presumably because we are going to treat them if they're diseased or not if they're normal. So the action that we're trying to decide is, should we treat the individual or not treat the individual? And the two possible underlying truths that we don't know are that the individual could be diseased or the individual could be not diseased. So in a way, we have four possible outcomes here, depending on which decision we make. It could be that the individual is diseased and we treat them, or the individual could be diseased and we don't treat them, or they could be normal, not diseased, and we could treat them, or they could be not diseased and we could not treat them. So those are the four possibilities. And the idea of the loss function is that it's going to say how bad, how sad each of those possibilities, each of those possible outcomes would make us. How sad would it be if we treated someone when they were not diseased and they were not diseased? So that's here, these four possible outcomes here. That little symbol there is a not. So we've got diseased and treat, not diseased and treat, diseased and don't treat, and don't disease, not diseased, sorry, and don't treat. Okay. So now, in order to specify loss function, we have to quantify how bad these things are. And of course, that might not be easy to do in general. That's one of the challenges of applying statistics to real world, is the difficulty of quantifying sometimes these hard to quantify things. But let's, as a matter of principle, it's still helpful to think about that as a way to do it, a way to rationalize decision making. So let's, and it's going to turn out that we don't have to specify as many things as it at first seems. So just to give an example here in this vignette, I assume I give these losses to these four possible outcomes that where big is bad. Okay, so 100 is the worst possible outcome. That's in this case, I've assigned that to the case where they're diseased and we don't treat them. Maybe this is a bad disease, and if we don't treat them, bad things happen. And okay, so let's not worry too much about what those losses mean for a moment. Let's just think about what I said, which is, if we assign these losses, we're going to choose make our decision to try and minimize our expected loss. So what we're able to do is either decide to treat, that's T, or not treat, not T. And so we can compute the expected loss under each of those two circumstances. So let's suppose we've computed our likelihood ratio and computed our posterior odds and our posterior probabilities based on the data and on the prior, and we got posterior probabilities of 0.5. So here, actually, I've omitted the data. Maybe that was a mistake here, but there's, I've got that the probability of the data is, the probability that the individual is diseased is equal to the probability that they're not diseased is equal to 0.5. That should there be posterior probabilities I've computed. So now I'm trying to make a decision. Should I treat them or not? Okay, that's the idea. Okay, so we've got to the stage where they're each 0.5, trying to decide whether to treat them or not. So what I do is, having assigned these losses, I can compute the expected loss if I treat. Z here is still unknown, but it's either diseased with probability 0.5 or it's not diseased with probability 0.5. And when I plug in the numbers, I get 15 as my loss. Whereas if I do not treat, I plug in the numbers and I get 50 as my loss. And since that's worse, I decide to treat. So that's the action that would minimize my expected loss under the modeling assumptions, under the prior assumptions, and under the loss. So there were three things that went into this computation, but at the end, the actual decision I would make is the one that minimizes what's called the posterior expected loss. That's this. The treatment here is what minimizes the posterior expected loss. So hopefully, if you go over the vignettes up to now, you can get these ideas clear in your head that, you know, there are three components. You have your loss function, you have your prior probabilities of the two classes, and you have a likelihood ratio, which would come from two different models for the two classes. And then you can turn the wheels of this calculation. You can use the models to compute a likelihood ratio. You can then combine the likelihood ratio with the prior to compute a posterior odds, and then you can, and a posterior probability, and then you can use those posterior probabilities to compute expected losses, and you can choose the action that minimizes the posterior expected loss. That's the basic idea behind the decision theory perspective in a nutshell here. So, but it turns out that you don't have to specify all those four numbers, because if you read through here, it turns out that if you add a constant number to all those losses, some constant C, it doesn't change the calculation. The action that minimizes the expected losses is not changed by adding some constant to all those numbers, and neither is it changed by multiplying them all by some factor. So because of those two, there are kind of 2 degrees of freedom there. That means you only really need to specify 2 of the 4 numbers. You can kind of subtract something to make one of them 0, and then you can divide. In fact, you can divide to make one of them 1. So it turns out that in order to do this calculation, or the result of this calculation, it only depends on the ratio of the losses of the 2 mistakes. So here are the 2 mistakes, if you like. Think about it that way. If there are 2 possible outcomes, in this case, there's 2 mistakes you can make, if you like. One is that you can treat someone who's not diseased, and the other is that you can not treat someone who is diseased. And so you can say, well, how bad are each of those 2 possibilities, and what's their, essentially, it only depends on the ratio of these 2 numbers. Okay, so it could be 1 2/9, or earlier 20 and 90. These will give the same answer. It just depends on that ratio. So you can see there's a lot of ratios coming in here, right? There's a prior ratio, prior odds, posterior ratio, the likelihood ratio, and now there's kind of a cost ratio, if you like. Cost, how much worse is it to make one mistake versus another mistake? Because all these decisions are trade-offs between those 2 kinds of mistake. So if you go through the math here, here's essentially the general calculation, and here it's framed in terms of 2 hypotheses, H0 and H1, but whereas before I was calling them models, but it's just a different term essentially for the same thing here. But this is maybe trying to phrase everything in terms of a language in statistics that is often used for hypothesis testing. So basically the idea is if you could make 2 types of mistake. You could choose H1 when H0 is true, or you could choose H0 when H1 is true. So there's not always an actual null and an alternative. So, it's sometimes helpful to think about these things without specifying one thing as a null and one thing as an alternative, like in the disease case, or maybe even better, the savanna elephant versus forest elephant. Neither of those is a null hypothesis, but in some settings, there is a null. It doesn't really matter here. The H0, H1 notation, I guess, suggests a hypothesis testing kind of setting where there's a natural null. It doesn't have to be the case. If you want to think about it as a particular one example that's helpful to you, then think about it that way. If you prefer the model-based approach without thinking about a null, you can think about it that way. The basic idea is there are two types of mistake here you can make. One is that you can choose 0 when 1 is true, and the other is you can choose 1 when 0 is true. Okay, so that's what these two costs. And if you do the calculation, what you find is that minimizing the posterior odds, minimizing the posterior expected loss means you choose H1, if this posterior odds is greater than this cost ratio. So ultimately, all that matters is that cost ratio in this that's it, the special case in the 2x2 table. So just to, if the costs of making two different mistakes are equal, that's a kind of a special case, right? Where you've got two possibilities, you're trying to choose between them, and you can make two different types of mistake. You could choose 1 when 0 is the right answer, or you could choose 0 when 1 is the right answer. And if you're equally ambivalent about both those, if they're both as bad, then you just choose the one that has the higher posterior probability. That is, if the posterior odds is more than 1, so we're doing the case where the ratio of the cost is 1. If the posterior odds is more than 1, you'll choose H1, otherwise you'll choose H0. So you just, it's kind of intuitively that if all the different mistakes are equally bad, you just end up choosing the class that has the higher posterior probability. Okay, so that's the end of that.